Look up at the night sky. It's a tapestry of darkness sprinkled with light, a vast canvas upon which countless stars tell their silent tales. Each point of light represents a sun, perhaps orbited by planets like our own. But have you ever stopped to wonder, where did it all begin? How did this grand, complex universe come to be? In the blink of an eye, the universe expanded at an astonishing rate, cooling as it grew. This wasn't an explosion in the traditional sense, like dynamite detonating in space. Instead, picture it as the fabric of space itself stretching and expanding in all directions at once. The universe, in its infancy, was a chaotic and scorching place. Temperatures were so extreme that matter as we know it couldn't exist, not even atoms. Our journey into the heart of the Big Bang begins in a realm so extreme, so foreign to our everyday experience, that even the laws of physics as we know them break down. This is the Planck era, a period so brief and energetic that it makes a billionth of a second seem like an eternity. Imagine, if you will, a universe squeezed into a space smaller than a single atom. At this time, the universe was a seething cauldron of energy, governed by both quantum mechanics and general relativity. The Planck era is shrouded in mystery, and our current theories simply aren't equipped to describe the universe at this scale. As the universe expanded and cooled, it crossed a critical threshold, exiting the chaotic realm of the Planck era. This marked the dawn of the Grand Unification epoch, a period when the universe was still unimaginably hot and dense. In today's universe, we experience four fundamental forces: gravity, the weak force, electromagnetism, and the strong force. But in the extreme heat of the early universe, these forces were unified, intertwined into a single, elegant superforce. As the universe cooled, the superforce began to separate, revealing the individual threads of gravity, the weak force, the strong force, and electromagnetism. The universe was still in its infancy, less than a trillionth of a second old, yet it was about to undergo a dramatic transformation, a period of exponential expansion, known as inflation. In the blink of an eye, the universe ballooned in size, growing from something smaller than an atom to the size of a grapefruit. Imagine a balloon with tiny dots scattered on its surface. As you inflate the balloon, those dots move farther and farther apart. This inflationary period, driven by a mysterious form of energy called the inflaton field, had several profound consequences. It explains why the universe appears remarkably uniform on large scales, and why the cosmic microwave background radiation has such a specific temperature pattern. As the universe cooled after the dramatic expansion of inflation, it entered a new phase, a period so hot and dense that it resembled a cosmic cauldron simmering with potential. This was the era of the quark-gluon plasma, a state of matter so extreme that it only exists today in the fleeting moments of high-energy particle collisions. Imagine a universe not yet populated by protons and neutrons, but by their even more fundamental constituents: quarks and gluons. Quarks are the tiny particles that make up protons and neutrons, while gluons are the force carriers that bind them together. In the extreme heat of the early universe, quarks and gluons roamed freely, interacting at unimaginable speeds. As the universe cooled below a critical temperature, a dramatic shift occurred within the primordial soup of quarks and gluons. The once free-roaming quarks, no longer able to resist the strong force's pull, began to clump together, forming the first protons and neutrons. This marked a pivotal moment in cosmic history, the birth of the building blocks of atomic nuclei. Protons, composed of 2 up quarks and 1 down quark, and neutrons, made up of 1 up quark and 2 down quarks, emerged from the cooling quark-gluon plasma. These particles, bound together by the strong force mediated by gluons, became the building blocks of atomic nuclei. While protons and neutrons were assembling in the cosmic dance floor, another class of particles, the leptons, played a crucial role in shaping the early universe. This family of particles, which includes electrons, muons, taus, and their corresponding neutrinos, would eventually determine the chemical properties of the universe. Electrons, the most familiar of the leptons, are fundamental particles that carry a negative electric charge and are responsible for the flow of electricity. In the early universe, electrons existed in a hot, dense sea, constantly interacting with other particles. The presence of leptons, particularly electrons, set the stage for the eventual formation of atoms. The universe, now a few minutes old, had cooled significantly since the frenetic energy of its birth. Protons and neutrons, those newly formed building blocks of matter, found themselves drawn together by the strong nuclear force. This period, known as Big Bang nucleosynthesis, marked a crucial step in the universe's evolution. The most abundant product of this cosmic cookery was hydrogen, the simplest and lightest element. Next in line was helium, a slightly heavier element with 2 protons, 2 neutrons, and 2 electrons. With the formation of the first atoms, the universe entered a period known as the Cosmic Dark Ages, a time when darkness reigned supreme. The universe, now a vast expanse of neutral hydrogen and helium gas, was devoid of stars and galaxies. Imagine a vast, dark ocean, its depths shrouded in an inky blackness. The only light comes from the faint afterglow of the Big Bang, the cosmic microwave background radiation. During this period, gravity began its relentless work, pulling together clumps of matter in the primordial gas. As gravity drew together the primordial gas clouds, the universe began its transition out of the cosmic dark ages and into a new era of light and brilliance. This period, known as the Cosmic Dawn, marked the birth of the first stars, colossal balls of hydrogen and helium that ignited in a blaze of glory. Imagine a switch being flipped, bathing a dark room in a sudden burst of light. The first stars, much larger and hotter than our own sun, blazed with an intensity that forever altered the cosmic landscape. Their intense ultraviolet radiation ripped through the surrounding neutral hydrogen gas, ionizing it in a process known as reionization. The universe, now ablaze with the light of the first stars, was about to embark on a new chapter in its evolution. The formation of galaxies, those vast, swirling collections of stars, gas, dust, and dark matter that populate the cosmos. Imagine a cosmic ocean, now dotted with countless islands of light, each galaxy a beacon in the vastness of space. These islands of light formed from the gradual accumulation of matter under the relentless pull of gravity. The tiny density fluctuations present in the early universe, amplified by the expansion of space, served as the seeds for these galactic structures. Over millions of years, these seeds drew in surrounding matter, growing larger and more massive. As these proto-galaxies grew, they began to spin, their rotation fueled by the angular momentum inherited from the swirling motions of the primordial gas. This rotation flattened the collapsing clouds into vast disks, setting the stage for the formation of spiral galaxies like our own Milky Way. Not all galaxies formed in isolation. Gravitational interactions between neighboring proto-galaxies led to mergers and collisions, shaping the morphology and evolution of these cosmic structures. These interactions, often violent and disruptive, played a crucial role in triggering bursts of star formation and sculpting the diverse array of galaxy shapes we observe today. Within these newly formed galaxies, another cycle of creation was underway, the birth of stars within vast clouds of interstellar gas and dust known as nebulae. Imagine a cosmic nursery where cold, dark clouds of hydrogen and helium, enriched with the remnants of previous generations of stars, provide the raw materials for stellar birth. Within these stellar nurseries, gravity again played the role of cosmic architect, drawing together clumps of gas and dust, increasing their density and temperature. As these clumps contracted under their own gravity, they heated up, eventually reaching temperatures high enough to ignite nuclear fusion in their cores. This ignition of nuclear fusion marked the birth of a star, a celestial furnace powered by the fusion of hydrogen into helium in its core. The energy released by this process counteracted the inward pull of gravity, creating a delicate balance that would sustain the star for millions or even billions of years. Stars, like our own sun, are the fundamental building blocks of galaxies, their light and energy illuminating the cosmos and providing the conditions necessary for life to emerge on planets orbiting them. The birth of stars in these stellar nurseries is a continuous process, ensuring that galaxies remain vibrant and dynamic over cosmic timescales. Section 3. The Cosmic Web, a tapestry of light and dark matter. As galaxies formed and evolved, they became interconnected by a vast, intricate network of filaments and voids known as the cosmic web. Imagine a cosmic tapestry woven from threads of luminous galaxies and invisible dark matter, a structure so vast that it spans the observable universe. This cosmic web emerged from the interplay of gravity and the expansion of the universe. Dark matter, a mysterious substance that makes up the majority of the universe's mass, provided the gravitational scaffolding for this cosmic web, its invisible tendrils guiding the distribution of ordinary matter. Galaxies, like beads on a string, trace out the filaments of this cosmic web, congregating in clusters and superclusters at the intersections of these filaments. The voids, vast regions of space seemingly devoid of matter, represent the underdense regions where the expansion of the universe has stretched the cosmic web thin. This cosmic web is not a static structure. The ongoing expansion of the universe continues to stretch and reshape the web, driving the evolution of galaxies and influencing the fate of the cosmos. Understanding the structure and evolution of the cosmic web is crucial for unraveling the mysteries of the universe's large-scale structure and its ultimate destiny. Section 1. Planetary formation, from dust to worlds. Within the swirling disks of gas and dust surrounding young stars, a new chapter in the cosmic story was about to unfold: the formation of planets. Imagine a celestial ballet, where tiny grains of dust, remnants of long-dead stars, began to clump together, their gravitational attraction growing stronger with each collision. Over millions of years, these dust bunnies coalesced into larger and larger bodies, eventually forming planetesimals, the building blocks of planets. These planetesimals, ranging in size from meters to kilometers, orbited their host stars in a chaotic dance, their paths intersecting and colliding. Some collisions were destructive, shattering planetesimals back into smaller fragments, but others were constructive, leading to the gradual accumulation of material and the growth of protoplanets, the embryonic stages of planets. As protoplanets grew larger, their gravitational pull increased, attracting more and more material from the surrounding disk. This process, known as accretion, sculpted the young solar system, clearing gaps in the protoplanetary disk and shaping the orbits of the emerging planets. The type of planet that formed depended on its distance from the host star and the composition of the surrounding protoplanetary disk. Close to the star, where temperatures were high, rocky planets like Earth and Mars formed from the aggregation of heavier elements. Farther out, beyond the frost line, where ices could condense, gas giants like Jupiter and Saturn accreted vast atmospheres of hydrogen and helium, becoming behemoths of the solar system. Section 2. The Spark of Life, a Cosmic Mystery. While the formation of planets is a remarkable chapter in the cosmic story, the emergence of life on at least one of these planets, our own Earth, is perhaps the most awe-inspiring twist in the tale. Imagine a sterile, lifeless planet, its surface sculpted by volcanic eruptions and bombarded by asteroids, slowly transforming into a vibrant biosphere teeming with life. The exact details of how life arose from non-living matter remain a mystery, but scientists believe that early Earth provided a unique set of conditions that allowed for this remarkable transition. The presence of liquid water, essential for life as we know it, along with a protective atmosphere and a stable energy source from the sun, created a cradle for life to emerge. Over billions of years, life on Earth evolved from simple, single-celled organisms to complex, multicellular life forms, diversifying and adapting to every conceivable niche on the planet. From the depths of the oceans to the heights of the atmosphere, life has woven itself into the very fabric of our planet. The emergence of life on Earth raises profound questions about the prevalence of life elsewhere in the universe. Are we alone in the vast expanse of the cosmos, or are there other planets out there where the spark of life has ignited, perhaps giving rise to beings as curious and inquisitive as ourselves? The search for life beyond Earth is one of the most compelling quests in modern science, a quest that could fundamentally alter our understanding of our place in the cosmos. The future of the universe. What lies ahead? Our journey from the Big Bang to the present day has been a tale of incredible transformations, a cosmic drama spanning billions of years. We've witnessed the birth of the universe, the forging of the first elements, the emergence of stars and galaxies, and the formation of planets and life. But the story of the universe is far from over. The cosmos continues to evolve, holding wonders and mysteries yet to be unveiled. The expansion of the universe, driven by dark energy, has profound implications for the future of the cosmos. As the universe expands, galaxies drift farther apart, their light redshifted across vast distances. The cosmic web will continue to stretch and evolve. The ultimate fate of the universe remains a topic of active scientific inquiry. Will it expand forever, or collapse in a big crunch? The answers lie in the properties of dark energy. Regardless, the universe will remain a place of wonder and discovery. New stars will ignite, planets will form, and perhaps life will emerge, adding to the cosmic story. Our journey of exploration has just begun, and the universe promises to spark our imaginations for generations to come.